Hello everyone, welcome to this XGSLab video where we will perform a grounding system analysis with the GSA FD module in under 10 minutes. So first we'll step into the project information. Here we'll say that this is a new substation and it's a 115 to 34.5 kV 100 MVA transformer. We have two T lines, two 115 lines, and four 34.5 lines. And other information that will be pertinent to this is actually the available fault current here. So let's go ahead and look at our EasyPower model where we can look at our power system fault availability. Here we see 8.84 Ka, and we'll just apply a growth factor of that to make this a simple 10 Ka. We'll assume a 0.25 second clearing time. And one thing I want to look at as well is the X over R ratio, because that'll affect our ground potential rise and corresponding touch and step voltages. So there's other information that we can add, such as the customer, designer, and the site's geographic location, but we'll go ahead and proceed by entering our reference standards. Here we will select IEEE standard 80 down the line. And then we are going to assert our frequency of our analysis, which is 60 Hertz in this example. That opens up this multi-layer icon where I can either manually enter a soil model or use the soil resistivity analyzer to take soil resistivity measurements, simply paste them into the software, and let XGSLab calculate the approximate soil model based off of how these measurements trend. And what we see here is a 3-layer model. What I'll also incorporate is any soil covering layer, such as a crushed gravel, that can affect my permissible limits. And we can see here at about that 16-foot depth is where we encounter this much lower 75 ohm meter soil resistivity. We'll save that as an image for our automated reports. And the next stage is actually incorporating our grounding system analysis into our design. And we can do this a couple different ways. We can either draft in the software or point to a DXF of a previously created model. Here we have red lines representing our grounding system, and these circular symbols representing the location of our ground rods. So in XGSLab, we'll navigate to that DXF, point to the associated layer that we want to import, and then assign the electrical conductors or electrical characteristics of those lines. Here we need to actually shift this down 1.5 foot. And that's going to be representing the buried depth of our ground conductors, because the CAD model may not represent the buried depth of our grounding system. We'll also want to incorporate these ground rods, and I'm just going to select this 3/4 inch rod, give it the rod tag name, shift it 1.5 foot into the earth, and assign these as 10-foot ground rods. And the final characteristic or final item I want to import is the civil works, and I just want to incorporate this as a background layer. When I import this, there are different tools I can use to make connections automatically with the software, but as we'll see, we're going to have a pretty clean importation from our existing CAD model. And with this, we now have a list of the conductors that were imported, and we can go to the draw view to see the visual representation of this grounding system. And one thing I noticed that these ground rods are not making contact with that lower resistivity layer. What I can do is go to my filters to just select those ground rods, refresh my view, and now I can select all of these ground rods and adjust them so that they are reaching 21 feet into the earth. This gives me a better contact with that soil resistivity layer that was 75 ohm meters. And this is probably going to help me mitigate my system or meet my touch and step voltage compliance criteria more easily. Let's return our view to show everything, and we will be able to see on this XZ plane that our ground rods, now being 20-foot length, are extending into that lower resistivity layer. The final thing we need to do is incorporate our fault current, which with a growth factor, we're just going to apply 10 Ka to this very specific conductor. Note that with the GSA FD module, the software is actually incorporating the self-impedance and mutual impedance of the entire system in its calculations. Hence, why we actually assign a fault current to a specific conductor, versus in more simplified tools, that fault current is applied to a grounding system or an electrode as a whole. With that, we can now do our debug and computation. What this will do is it's looking to determine if we have any conductors that were overlapping in our CAD model, or conductors that were isolated from the rest of the system when it really should be interconnected. And if that were the case, our debug tool would flag that to the user. But here you can see we've progressed into the computation. And in about 19 seconds, we can see our ground potential rise associated with this system is about 17 kV, and our system impedance is about 1.7 ohms. Taking a look at our line calculation criteria, we can get a preview of our touch and step voltage values. I want to calculate the touch and step voltage limits based on IEEE 80. And then I'll navigate back to that line calculation here. And I'm just going to draw across this area so that we can get a slice of what our touch and step voltage values look like in comparison to our permissible limits calculated from IEEE standard 80. I'll incorporate a surface covering layer, and when I look at my plot, what I see is this solid red line is above the dashed red line, representing my touch voltages are exceeding my touch compliance limits. One way to work around that is either adding more mitigation, or we might do a more detailed analysis by incorporating a fault split factor. Here we know our system impedance is 1.68 ohms. We have injected 10,000 amps. Our system analysis is at the 60 hertz, and we have 0.25 second clearing time with a 7.6 X over R. Based off of the power system interconnection, we can calculate or use the nets tool to develop the equivalent impedance of the shield wires that are associated with the transmission line or the distribution neutrals. And that tells us that we have about 4,159 amps that's going to produce a ground potential rise at our system. Now I can take this and put that back into my analysis, or I can just use this simple scaling factor of 0.41, and what we'll see is our ground potential rise is reduced to about 7 kV. And we can see this if we look at the metallic potential of our grounding system. Now that we've reduced the ground potential rise associated with our grid, let's take a holistic view of our touch and step voltages. So I'm going to my area calculation, encompassing the area that I want to evaluate, and I'm adjusting my step length to be 3 feet. Meaning that every 3 feet, we're calculating the Earth's surface potential directly in this software. These values are what's used to calculate our touch voltages by comparing the Earth's surface potential to our metallic voltages, or they're used to calculate our step voltages by comparing one calculation value to another. Obviously, these are adjustable. Higher number of steps result in a more accurate analysis. It does take longer to calculate those, and typically we'll find that the step length in the range of 1 to 3 feet is acceptable for a reasonably accurate analysis. About 10 seconds more here and we'll have our results. So if I navigate down to the touch and step voltage group box and plot my safe areas plot, what we'll see is a green indication of where we have met touch and step voltage values. Yellow indicates where we're exceeding compliance limits for touch voltages. And in this area, we might incorporate some mitigation or rebar, but we'll progress into reporting our values. So here we can go to our automated report and we can see we have a table of contents, our grounding system model, or our pertinent information about our grounding system, the soil resistivity information, soil model, and of course, our safety plot. So this represents our grounding system analysis in approximately 10 minutes. And if you are interested to learn more, please feel free to email or call us. Thanks.